For this homework question, we have a 5-kilogram box resting on a spring. The spring is compressed by 2 centimeters, and we want to find what is the spring constant of the spring. So we'll start by drawing a free body diagram of the box. We could draw it right on top of the picture, or we could draw it separately. So on our box, the spring is compressed, the spring is squished down, so the force must be pointing up. So there's our spring force. We know that the weight of the earth is downwards on the block because the earth pulls down. After the free body diagram, we'll write our Newton's second law. Sum of the forces in the y direction is mass times acceleration in the y. What we have in the y direction is our spring force minus our weight equals 0 because the box is resting on the spring on the floor. And our spring force, the magnitude of that is given by Hooke's law. It's positive because it points up, so we have plus kx minus mg equals 0. We want to solve for k, we'll bring our mg to the other side, divide both sides by x, and we get mg over x. Put in our numbers, 5 kilograms times 9.81 meters per second squared, divided by x, 2 centimeters, so we'll write that in meters, 0.0200 meters, to get a spring constant of 2,453. And then the units are newtons per meter. So there's our spring constant for that spring. Next, we know that a person ties a rope to the crate and applies a 25 Newton force to try and lift the crate. So what's going on now? Now we have our box. We're trying to lift it, so we have a tension force up and a weight force down. We know that for sure. First question is, does the crate lift off the spring? So to answer that question, we'll have to think about the relative value of tension and weight. If tension is bigger than weight, then it will lift. If tension is not bigger than weight, if the tension is smaller, it does not lift. So our tension is 25 newtons, that's the upward force. Weight is equal to mass times gravity, equals 5 kilograms times 9.81 meters per second squared. So the weight force is m times g, that's 49.1 newtons. So we see that we have the case where the upward force is 25 newtons, the downward force is 49.1, so it does not lift off the crate. So tension is less than weight, so it does not lift. So we'll draw a free body diagram. So we have the tension force points up. So this part was to answer if it lifts or not. Next we'll draw our block. We have the tension force points up. We have the weight force points down. The spring force is a little bit complicated. Does it point up or does it point down? And it depends on the compression or elongation of the spring. If the spring is stretched, if it goes upwards, then the spring force pulls it back down. If it's compressed, then the spring force holds it up. So let's say that the spring is helping to hold it up, F spring. If we're right about holding it up, then we'll get the right sign for our x value, we'll get the expected value. If we're wrong, if the spring force pointed down, then we would get a negative sign that we wouldn't expect. So here's our free body diagram. Let's do the sum of the forces in the y direction is mass times acceleration in the y direction. So we have the tension plus the spring force minus the weight equals 0. 0 because it's still on the spring. We're lifting it a little bit, but it's not moving, so the acceleration is 0. And our spring force is k times x, our weight is m times g, so we'll put those in there, being careful with our signs. We've assumed that the spring force is positive, so we have positive kx. So our tension is 25 newtons plus our k, which is 2,453 newtons per meter, times x minus mg, which we calculated up here, 49.1 newtons, equals 0. Now we can solve this expression for x. So x is going to be, we'll bring our 49.1 over to the other side, 41.1 newtons minus 25 newtons. Bring our 25 to the other side. Then we divide both sides by 2,453 newtons per meter. do this on the calculator, and we get 0.0098 meters, or 0.98 centimeters. So this is positive, so the spring force is up. So even though we're lifting it with a force, the spring must still be a little bit compressed. We haven't lifted enough that it's going to come off the spring. So by how much does the spring stretch past equilibrium height? Turns out the spring is still compressed compared to the equilibrium length.